helium sources. Part 1 of this series discusses helium exploration today, the differences between proven and prospective reserves, and the technologies enabling effective helium exploration.
Evonik, power to create.
Getting the discussion underway with me today is James Weaver, petroleum engineer, geologist and CEO of Aon Petroleum Consultants. James started Aon Petroleum Consultants in 2018 with an extensive background in reserves estimation and evaluation, production optimization and economic analysis. This background included a significant amount of time evaluating tight gas sands, coal seam gas, shale oil, CO2 source reservoirs, and helium recovery projects. And eager gasworld readers will know that James recently authored a feature on the differences in helium reserves and resource types. We asked James to join us here today to set the scene on helium exploration, decipher what the different kinds of helium resources are down in the ground, and help you better understand what matters amidst all the chatter. James, welcome to the show. Now, if we took all of the headline numbers out there related to current and future helium exploration projects, we might well think we're sitting pretty on a very bountiful market ahead. So if you can, explain to us what we're looking for when it comes to proven reserves and contingent and prospective resources.
Thank you, Rob. Yes. Right now, we've got about a dozen companies or so out there exploring for helium primarily. In the past, most helium was found by accident looking for natural gas. And that's just not a way to really find additional helium. We really need to go out and look for helium on its own. And a lot of times these companies will put out press releases or they'll put out items on their website or even reports. And they'll use terms sometimes like technical recoverable reserves or potentially recoverable resources and terms like that, which really, those terms I just mentioned really don't have any meaning. So what we really need to do is see what kind of terms should be used in those press releases and what the investor can look for when he sees those terms and how to make some sense of them. All right. So now, because when it comes to commerciality or the potential to recover those resources, there is a lot of difference between reserves and resources. So right now, there are several schemes out there that are used to report reserves. Here in the United States, for a publicly listed company, the most common one would be the Securities Exchange Commission definitions, and those only cover reserves. They don't cover resources at all. In Canada, we have the National Instrument 51101 that's used to report reserves and resources, and that's similar to their mining 43101 mining reporting. And then the one that's used most common around the world and is gaining more traction over the years has been the Petroleum Resource Management System. And we're going to call that the PRMS. But right up front, we've got to say, there is no official definition of helium reserves and resources because the PRMS only concerns itself with oil and gas reserves and resources. In fact, it specifically says in there that it doesn't concern itself with non-hydrocarbon constituents like carbon dioxide, helium, and sulfur that are sometimes found as a byproduct of oil and natural gas production. So what we are going to do is we're going to use the guidelines of PRMS to define helium resources. And in some reports, you will see a little disclaimer in there that says, although there is no official definition for helium reserves and resources, we are going to use the definitions of PRMS or the guidelines of PRMS we're going to use similar guidelines of PRMS to actually calculate and estimate those reserves and resources for helium. And that's what most consultants will do. There is some talk now about, adding in the next revision of PRMS, those non-hydrocarbon constituents. So we'll have to see if that actually happens in 2022. Now, we're going to also have to say that PRMS defines three types of resources: reserves, contingent resources, and prospective resources. So I'm going to talk about each one of those individually and what the criteria are and the hurdles are for each one of those categories. So let's start out with reserves, because almost everybody will just say, oh, I've got reserves of this much gas or this much helium, when really it might not be reserves, because reserves is a pretty high bar to be set, right? So the official definition in PRMS is those quantities anticipated to be commercially recoverable by application of development projects to known accumulations from a given date forward under defined conditions. Now, a given date forward and defined conditions, that's interesting. A given date forward is common to all definitions. We need to have a start date before we can have anything else. When is this thing going to start, right? Because PRMS, unlike prior reserve definitions, is what we call a project-based reserve system. And by that, I mean you need to have some project or some anticipated development plan to go get those reserves and resources. You can't just say, oh, we have some acreage over here and we're just going to put a number on it. You have to actually have some plan to either explore that acreage or develop that acreage before you can actually have reserves or resources under PRMS guidelines. So one thing about reserves that I just mentioned is known accumulations. That means you have to know about it. It has to be discovered. And usually that's done by drilling some wells into the reservoir, right? It also needs to be recoverable. I need to be able to get it out of the ground, right? And it also, the biggest hurdle for reserves is it needs to be commercial, or it needs to be economic. You need to make enough income off producing it to pay back your expenses and your capital. And that's something that in the past we didn't really worry about too much, but under PRMS we actually have to do that. And then the other thing it needs to be is it needs to be still available to recover. It can't be already produced somewhere, right? It still has to be available to produce it. Now, reserves can be developed or undeveloped, and by that I mean developed is I've spent the money and I've got a well drilled, or I've got a project there that I can produce out of. Undeveloped means I still have to spend some money to go get it, right? Now, in the developed reserves, you can be producing or non-producing. I could have drilled the well, but it's not online yet, which would be non-producing, or I could be producing it already, okay? And undeveloped is something like a well yet to be drilled nearby that actually can be drilled in the future, and that would be an undeveloped reserve, all right? Now, we also have something called a range of outcomes. So we have a proved reserve, which means you're 90% sure you're going to get that amount of volume or greater. A 2P reserve, or proved plus probable reserve, we call that, means you're about a 50% chance of getting that number. And a 3P, or proved plus probable plus possible reserve, meaning you can get 10%, there's a 10% chance. So we have a range of outcomes there. Now, reserves have a low risk of commerciality because we have to prove they're commercial in the first place to be a reserve, and they have a low risk or a high chance of recovery because we have to have a lot of information to do reserves. We have to have some test rates. We have to put together a development plan. We've had to analyze the reservoir to see if there's enough, helium there to produce. So that's one of the other things that qualifies reserves. There's a lot of detail and a lot of data required to do reserves. The economics or the commerciality test is usually done on the proved plus probable, or what we like to call our best estimate case, right? So if that's satisfied, then typically we can put reserves on our books. Now, the next category that we're going to talk about, or the next classification rather, is contingent resources. Contingent resources are sort of like reserves, but there's something in the way of them becoming reserves. Typically, it's not enough production data, or you don't know the size of the reservoir, or maybe you don't even know if your company is going to invest further to develop it into a reserve, right? But the official definition is those quantities as of a given date to be potentially recoverable from known accumulations by application of development projects, but are which not currently considered to be commercially recoverable owing to one or more contingencies. Now, potentially recoverable, let's talk about that a minute, because that's really an important term, right? So it has to be discovered. We have to know it's there. there. So most likely we've drilled a well into the reservoir. Potentially recoverable. Boy, that covers a lot of ground. It can be, a puff of gas coming out of the ground, but I haven't tested it yet. It could be a lot of gas coming out of the ground, but I'm in a remote area, so I don't know if I can connect up to anything to actually sell this product. So, contingent resources is a big, giant basket of stuff. And that's why any contingent resources report needs to contain what the contingencies are. Why isn't this a reserve? What contingencies do I need to overcome to move this into the reserve categories, right? So there's no requirement for economics under contingent resources. So it has kind of a mid-range chance of commerciality and about a mid-range chance of recovery, because it can go either way. A lot of third-party engineering firms that do contingent resource estimates consider contingent resources to be a holding pattern. In other words, I'm either going to do something to move it into reserves, or I'm going to try those things and it's unsuccessful and I have to move it off the books. So it's either going to become reserves or it's going to go in the trash can, right? So those are the two considerations. We also have a range of outcomes we estimate for that. Now we have the 1P, 2P, and 3P for reserves. Under contingent resources, we just replace the P with the C, and we have 1C, 2C, and 3C. Similarly, the 1C, 2C, and 3C would have a 90%, 50%, and 10% chance of recovery for that. A lot of times remote locations are found with helium in them, right? So we don't know until we get ready to put a plant up that, it's not reserves even at that time. It could be contingent resources, because one of the things you have to have is a market for the product for it to be a reserve, right? Commerciality, I need to be economic. Well, until I put a plant in, I don't know necessarily if that's going to be economic. So a lot of times for helium projects, contingent resources are out there for a long time on the books, because we've got to drill enough wells to justify a plant, to have enough rate, and we have to have enough reserves there to justify putting a plant in, say, for a 10 or 15-year period. So it might take a while to get from contingent resources to reserves for a helium project. Now, the last category I'm going to talk about are prospective resources. And you say, well, wait a minute, what's the difference between prospective and contingent? Well, it's a major difference. One is contingent resources have to be discovered. Prospective resources are undiscovered. So maybe I've got, some geologic mapping, and I've got some seismic information, other information, and I've got a structure there, but I haven't drilled a well there yet. But the zone that I'm looking for is there. So it's undiscovered, but it has a likelihood of potentially being, a reserve at some time, because all the items that I need to have there, structure and the zone and, that kind of thing, are there. So therefore, we're going to call that a prospective resource. And it's simply defined as those quantities estimated as of a given date to be potentially recoverable from undiscovered accumulations, right? So prospective resources undiscovered rather, contingent resources are discovered. And these have pretty low chance of commerciality because I haven't drilled anything there yet, right? So I can't put a high chance of recovery on those things because I haven't even tested the well yet, right? Now, similar to reserves and contingent resources, we do have a range of estimates. We call them 1U, 2U, and 3U. And again, they have a 90, 50, and 10% chance of recovery. Now, because we don't know a lot of things about maybe what the reservoir looks like in that area, we typically run these things using a statistical or a Monte Carlo analysis. So we put ranges on all the parameters that we need to know about, like the thickness of the zone, the water saturation, the porosity, the aerial extent of the reservoir we might see out there. And we run all those things in a Monte Carlo simulation, and we come up with a log normal distribution. We're multiplying parameters. We're multiplying the height of the reservoir times the area of the reservoir times the porosity of the reservoir. Anytime you multiply parameters, the outcome on a statistical basis is going to be a log normal distribution. And from that log normal distribution of the outcome, we pick the 10, 50, and 90th percentiles, and those are our 1, 2, and 3U outcomes. So to put it all in a summary here, when you're looking over these reports, let me just give you a few keys that you want to look for. If you see the word reserves in there, they're discovered, And there should be some economic discussion in that report because they've had to run economics. They've had to done quite a bit of detail there, as to what's gonna be in there. There's also most likely going to be a development plan in there with some timing because you can't really run economics without doing those kind of things. One other thing to keep in mind is if it's a report that has contingent or prospective resources, keep in mind, and usually there is a disclaimer in the report, that there's a possibility these could never become reserves, right? In other words, those contingencies could never be overcome to move the contingent resources to reserves, or I may, undiscovered, I may think I've got something there that might be discovered in a prospective resource that actually doesn't get discovered. So it's never going to be a reserve. You cannot add reserves and resources together, right? Once they're in those categories, that's it. You can't add them together. If it says it's undiscovered, if it says it's undiscovered, it's prospective resources, right? They can't say, well, it's not discovered, but it's a reserve. No, there's no such thing. If it's undiscovered, it's automatically prospective resources. And if it's not economic, it can't be a reserve. All right. So those are some things to keep in mind. And I hope that's been helpful. I know I went through it pretty quickly, but the article's out there in GasWorld. You can read it in more detail, and there's a table in there that has a comparison chart that might be useful to some people when they're going through these reports. You can have that handy and just kind of check off the list and make some notes for yourself. I'm open for questions at this time, and I'll turn it back over to Rob.
Absolutely. Thanks there, James. That's some really fantastic detail. And I think we do need to better understand that as the market continues to evolve. So absolutely fantastic. Appreciate this is on a very simplistic level, but just to clarify, would you say we're better to look for the proven reserves for a more realistic picture of the future market capacity?
When I go back over reports and estimates that I've done in the past and do kind of a forensic look back to see what numbers actually came out of a given field, what I find is that the number that I actually come up with is probably closer to the proved plus probable reserve number than it is the proved number, because over time, what you see is you get more and more information. The proved number tends to move up, and the proved plus probable number tends to move down slightly. But I think that would be a more realistic look at what we can use as future, capacity and expectations.
Okay, that's great, James, and thanks again. That's really insightful. It's really great to drill down into this. Pardon the pun.
Yeah. Well, thank you.
Evonik, leading beyond chemistry.
Now, my next guest is Alex Evans, Business Development Manager of Membranes at Evonik Membrane Technology. As we've just seen from that short clip, Evonik is a world leader in specialty chemicals, operating in more than 100 countries around the world. The group's Sepuren membrane technology has really caught the eye in the biogas business of late, and I'm delighted to say that we have Alex here to tell us more about that technology and the role of membrane technology as a whole in helium exploration. Alex, welcome to the webinar. Perhaps you'd like to begin by telling us about Evonik's membrane technologies and Sepuren High Select in particular.
Sure, and thanks for having me today, Rob. I really appreciate the opportunity to speak in this setting. I'd like to ask for your help if you can show those a couple images that I prepared ahead of time to help me explain how a membrane works. So a membrane in this instance, what I mean is a bundle of hollow fibers that separates gases based on, or gases on a molecular scale. So this bundle of fibers looks a lot like spaghetti to the naked eye, but in reality, each strand is actually hollow and has permeable sidewalls. So faster gases such as helium, hydrogen, CO2, those are able to permeate the membrane wall, while others remain inside, such as methane and nitrogen. So you can kind of think of each strand as a pipe with walls that are permeable to specific molecules, which is what I'm showing here in the images on the screen. The gases enter in the center of the fiber, then specific gases such as helium are able to permeate the walls while others stay inside. You can also think of this as a filter on a molecular level for specific gases, all with no moving parts. So as you were saying, around 15 years ago, Evonik invented a new high-performance polymer to use as a gas separation membrane. We entered the biogas market with this new polymer and achieved pretty quick success. The polyimide fiber that we use, those fibers are extremely robust, which has proven to be very valuable in harsh conditions such as with natural gas. Since then, we've tuned this polymer for new applications and now serve the nitrogen generation, hydrogen purification, natural gas sweetening, and of course, helium purification markets as well. As we've already described a little bit, we're in this world now of helium shortage 3.0, where the BLM has reduced their allocations and projects in other parts of the world are delayed coming online to produce more helium. So in the past 2 to 3 years, global helium supply has not been large enough to keep up with demand. The BLM's actions have forced helium consumers to look for individual suppliers or individual sources of helium. And today, nearly all helium comes from rock formations very similar to natural gas. So this is going to be the focus of where our membranes are relevant. So in some cases, we know the helium is there, but owners need to maybe find a cheaper way to produce the gas from their assets. Many sources of helium were found, as we've already said, when searching for natural gas. But analysis of test drillings or well samples showed very small amounts of hydrocarbons and maybe 1 to 2% helium along with it. So helium alone historically has not been enough to make those wells worth exploiting in the past. And we're also constantly improving our geological and prospecting knowledge, so more and more sources of helium are identified over time. And like James was saying, some of these can be especially challenging if they're in remote locations. So what I've described here is basically the beginnings of the Minn-Kota helium project, in case you're familiar with it. It's in Saskatchewan at a very remote location, few hydrocarbons, small amounts of helium. And I'll come back to that later on. But in some cases, projects aren't always economic because the price for helium is either not high enough to offset the large costs associated with this, or maybe in addition, there's not enough hydrocarbons in the gas to make the project worthwhile from a natural gas perspective. So to improve project economics, you can of course either attempt to increase your revenue, reduce the costs, or both. So I'm here to present membranes as a solution to significantly reduce the cost of producing helium and efficiently producing high quality helium directly at the well through a hands-off passive process. So by nature, as we've already said, Evonik is a specialty chemical company. We develop the best polymer in the world for membrane-based separations, but we need a partner to engineer a useful system. So a membrane by itself is not yet useful. This is where our collaboration with Linde and Linde Engineering comes in to integrate our membranes into their gas processing plant designs, which Patrick, I'm sure, will speak to further. But membranes create a very economically attractive case for helium sources which have not been historically viable to exploit. Coming back to Minn-Kota, the facility there is a great example of how you can produce 99.999% pure helium directly at the well using a membrane solution incorporated into Linde's designs. So if you're curious about this kind of design, I'm sure Patrick is going to touch on it some more. But Minn-Kota is not the only facility in the world that membranes would make sense to be used with, right? So membranes are a viable solution wherever helium needs to be purified. So with that, thank you, Rob. I appreciate it. I'll turn it back over to you.
Great, thank you, Alex. So you just said or hinted quite often, we know the helium is there, but owners need a cheaper way to produce the gas in some cases. So am I right that the Sapura and Noble membranes offer quite a compelling advantage in operating costs for helium production plants?
Yes, absolutely. I'm sure Patrick will discuss this as well. Membranes allow for a system that can be operated with very little intervention, which is advantageous, especially in remote locations like Minn-Kota. Since there's no moving parts in a membrane, you can imagine that they require very little supervision and even less maintenance. This enables even helium wells which do not contain hydrocarbons to be exploited economically.
Okay, well, I'm sure we'll hear more from you shortly, Alex. Thank you very much. Now, as Alex has alluded to, my final guest today is Patrick Schiefman from Linde Engineering. It's often one thing hearing statements about a given technology, but it's another altogether to get a case study of that technology in progress, and that's exactly what we have here. Linde has been working with Evonik's polymer-based membrane technology in gas separation and purification plants for several years. And Patrick can testify to both its role and efficacy with a helium purification plant in Canada. Patrick, welcome to the webinar. Now, you're a chemical engineer, you've got a PhD in membrane technology, and you've worked at Linde Engineering in R&D, absorption and membranes for 6 years. So you've clearly got the credentials in the field. Tell us a bit about helium exploration today and how these kind of membrane technologies can change the game in exploration and purification.
Yes, Rob. Thank you very much also for having me and giving me the opportunity to talk a bit not only about the membranes, but how we included this membrane, where you heard the details about the separation from Alex, how we included this membrane in our toolbox. We at Linde Engineering have a toolbox of gas separation technologies, which PSA technology, pressure swing adsorption, we have liquefying, we have air separation plants. So, and also now we introduced the membranes in our portfolio. And in this specific project, which Alex mentioned in Mankota, we combined those technologies into a new hybrid system, which really changed the game in helium separation and purification. So, as most of you know, and also James and Alex mentioned already, helium has been mostly found by accident in natural gas reserves or in natural gas wells. So, and this is also the main gas where it comes from, or the main source. So helium is a byproduct of LNG production, or a big part of the helium that we use. An LNG plant, which is liquefying natural gas. So you have to liquefy gas, which costs a lot of energy, it costs a lot of capital costs, and those plants need a very large amount of feed gas to be economically viable. And usually there are in locations where there is a lot of natural gas, which is methane. So if you have a well or source where there's no methane, it was not useful to try to take out this helium, as it is the case in this case where test drilling while searching for natural gas reserves, they found that there's approximately 1% helium in the gas, but no methane. So, okay, in the past they could not do anything with it, closed it up again, and left it alone. And now somebody found this and said, hey, we can produce this helium. It's a remote location, so it's no natural gas methane in it. So how do we purify this helium? Because liquefying just doesn't make sense to do this. And then we came with our technology where we combined this membrane with this superior selectivity, which is unique on the market for glassy polymers, and our PSA technology to produce this 99.999% helium from 1% in the feed. And actually this 1% is already our comfort zone. So we could even go lower in the helium concentration. And in this process, we use a first membrane stage, which removes the helium from this nitrogen and methane gas to the permeate, increases the concentration to a level that the PSA, a pressure swing adsorption plant, can produce this very pure helium and have a tail gas with also the remaining helium. In order to further increase the recovery rate of helium from this plant, we can introduce a second helium stage downstream of the first membrane stage. We use a second membrane stage, and we remove all the remaining helium from this gas. We go down to levels of 100 ppm. That's absolutely no problem. In some cases, we could even go lower. And this with the high selectivity, so we increase the concentration up to 10-fold from the feed to the permeate. And then we take the second permeate, combine it with the tail gas from the PSA, and we recompress it, and we recycle it upstream of the first membrane stage. So, and in this way, we again increase the concentration to the first membrane stage, which makes this first stage more efficient. It increases the selectivity, and it increases the recovery rate of the overall plant. So this way, we can reach up to 95 or even 99% of recovery rate from the helium. So that means that 99% from the helium in the feed gas will end up in your product, which is quite a lot. And this can make such resources or such reserves more economic than they have been before. And the thing is that due to this high selectivity of the membrane, this recycle flow is quite small compared to existing membranes before, or membrane materials that existed before on the market. So the compressor we need is much smaller than with other membranes or other materials, which reduces capital investment, which reduces energy costs, and which makes this plant even more efficient and more economic. This plant, there could be different combinations of membrane stages. There can be 3 membrane stages. There can be only 1 membrane stage. We have pre-treatment, which is also mostly adsorption technology, which is also in-house in our toolbox. So we can design completely the plant from more or less from the well, from the dry gas to the product. And in this case, the product is compressed. The helium is compressed and filled into high pressure tube dwellers, and they drive to the next liquefier or to the next consumer, depending if the consumer is quite close and the helium is pure enough, then you can directly use it as pressurized helium. If not, if you have to transport it further away, then you need a liquefier, so you can bring it to the next liquefier. And this is kind of the future scenario that we are thinking. So these remote locations, really remote. I mean, it's not like 100 kilometers, but it's like a 5, 6, 7 hour drive from the last part of civilization to the plant. To have multiple of these plants which can operate automatically. So you don't need an operator on site. The startup takes about 2 hours from cold to full operationality, so that's quite impressive. And you don't need much maintenance. Only the compressor needs some maintenance. That's the only part with moving parts. So this needs to be maintenance. The membranes, we don't need to exchange them. They are so stable. Evonik has this special technology to produce these membranes. They are very stable against higher hydrocarbons, against trace components, CO2, H2S. All these components, of course, they change the performance of the membranes, but they don't destroy the membrane, and you don't need to exchange it because it keeps its capacity and its selectivity over years. And it's a bad business for replacement of membranes because you don't have to replace the membranes. So you sell a product that you cannot sell again. But in the end, I mean, we're quite happy with this kind of plant and with this hybrid solution because we really have a game-changing thing now, this plant. I think it will change the helium market. And when you have this remote located helium plants, which are operated more or less independently, you just need to get the trucks at some point to fill trucks to the next liquefier. But then you can maybe also construct a liquefier somewhere where before it didn't make sense because all helium was too far away and there was not enough helium in the surroundings in order that it make economically sense to build this liquefier. So yeah, this is basically this process that we have. As I said, it is all in-house technology from Linde. The membranes is from Evonik. We have a very close cooperation, which is very fruitful. And I also think that the development of this process could not have been made this way without this membrane. And I also think that the cooperation with Evonik helps Evonik to understand and to implement their membrane and optimize their membranes. So at this point, I think this cooperation really is also the thing that made this improvement possible. And then thank you. Back to you.
Thanks, Patrick. You used the words "change the game" very early on there. So is it then a really noticeable difference in purification that we're seeing here with these membrane technologies at play?
Yes, sure. So as I said, this membrane, it has a very, very high selectivity, and it's double of membranes that were on the market before. It's incredible high selective. The capacity is very good. The stability is very good. So that's why this membrane, this material, and the optimization of the material and the production of the membrane. I've seen the plant where they produce the membrane cartridges, and it's impressive. This is not a workshop. It more looks like clean room. Yeah. Sure. And these membranes, it's a high quality product, and this only because of the selectivity and this capacity, and because of the knowledge of the membrane, and we know how it reacts to different components, we can design this plant the way that it works as it works now, so efficiently. That hasn't been possible with membranes before, because from 1% helium, if you have a membrane which increases the concentration 3 times or 4 times, it doesn't make sense, because it's not enough for the PSA. You need a membrane which has this selectivity and produces this high concentrated permeate in order to feed the PSA, so the PSA can work and produce the helium. And on the other hand, this recovery stage, which I mentioned, the second membrane stage, is also very important, because you could maybe with another membrane, you could have one membrane stage, you take out 20% of the helium, you produce your pure helium, but you lose 80%. And this is 80% that go to the vent or to the natural gas pipeline and up the chimney in the from the next consumer. And then the helium is lost to the atmosphere, which is, a pity. So, and to increase this recovery of the plant, you need another membrane stage. But if this membrane stage doesn't have a high selectivity, you recycle most of the nitrogen and you don't recycle helium. And if you recycle nitrogen, you dilute your helium in the feed, and the first helium stage doesn't work anymore. And that was the problem with plants of type before. They needed multiple helium or multiple membrane stages, multiple compressors, a PSA. And if you have 2 or 3 compressors in your plant, which are quite huge or quite large, then the economics go down. You have to have 2 compressors and not only 1, and this makes it not viable anymore. So this was what I call the game changing for this kind of process.
Sure, and it sounds like we're absolutely maximizing the margins here, which is fantastic. I'm sure the helium business definitely needs that, as we could all agree. Thanks, Patrick. Thanks again, and now we'll throw the floor open to Q&A.
Power to create.
Okay, welcome back. And now let's move on to those questions. I'd like to begin with a question to the whole panel, if we can. And that question is, how different or perhaps more advanced do you think the helium exploration and purification business is today compared to, say, 10 or 20 years ago? Has it moved on because we've had to move on and basically dig a little deeper in terms of the product we're recovering? James, perhaps we'll come to you on that first.
Well, I can speak to the exploration side. We have 2 good experts here that I just really enjoyed listening to that can talk about the processing side a lot better than I can. But on the exploration side, I would have to say this. As I mentioned before, and it was brought up a couple of times, that we only found helium by way of looking for natural gas, and it turned out to be, hey, we found some helium in the gas. Well, about 10 years ago, we decided to come up with an exploration model for helium based on what one of my clients told me. He said, there's no such thing. There's nobody looking for helium at that time, 10, 15 years ago. So I started looking at, how we find natural gas and the models we use there, and quickly concluded that those were not going to work for looking for helium. Places you find natural gas where you have a lot of hydrocarbons being generated tend to dilute any helium that you might have, even if it's a helium generation area, and therefore dilute it to a point where you can't actually recover it. So we developed a helium exploration model, and we tested it against a lot of discoveries to try to, hone in on what a good model would be. So we actually have some companies out there now looking specifically for helium. They've got their own models as well. And I think that is the biggest difference, say, in exploration that's happened over the last 10 years.
Definitely a marked difference, certainly in my time covering this industry. Alex, would you have anything to add?
Yeah, sure. So from the processing side, the biggest change in the past 10 to 20 years, I would say, is that we've widened the circle, so to speak, to define which helium projects are or would be economically viable. So since it's no longer the case that you must have high levels of helium and some methane that you can exploit, now that the membranes allow for a process or a well where only helium, where a well with only helium could be viable, now suddenly more of our known assets, so to speak, could be economically viable. So we've widened the circle. We've defined a new avenue that the market can take to produce to bring helium to market.
And finally to you, Patrick. I mean, I guess you've kind of touched on this already, but what differences have you seen, between then and now?
The difference is that in the past 10 years, or at least in the past 6 years, where I'm really involved in this topic with membranes, that the number of requests for this kind of plants increases. So, and you see that more and more of these gas compositions are not methane anymore, but they are nitrogen. There's only little methane in it. There's more and more of these compositions, more and more of small wells. It is remote, small gas sources. So it doesn't have to be millions of cubic meters per day or per hour, but it's small production sites where it could be viable to do this. And this, of course, is then you need a high recovery. You want a high recovery in order that it makes sense. Because we cannot waste it anymore, the helium. I mean, it's too expensive to just vent it to the atmosphere. Yeah, and there I see that the development of this technology and of this kind of plants and of these processes, they increase and they become more. And this is, for me, the indication that there's a lot of development has been done and is done, not only in the engineering, but I guess with all gas companies are on the same way here.
Great, thank you, gentlemen. So let's move to the first question from our audience today, and that comes from Inrul, who asks, is it possible to implant this system into existing plants? What's the minimum plant capacity needed to get helium in this process? I'm not sure if Alex or Patrick could answer that question.
I try to answer it. So there's no real limitation, actually. I mean, I don't have a number right now, but the membranes, you can scale them linearly, the membrane surface area that you use, and the PSA is very flexible. I mean, the smallest PSA, we can still run it in a turn down below 50% of the feed. So it can be integrated in existing plants, for sure. It can be integrated in pipelines. If you have a pipeline, if there's natural gas and there's a very small amount of helium, you can use membranes to extract most of the helium, and then you only have a small stream that you have to process further. It's not especially that you have to produce this 99.9% helium, but you could also produce 10%, a 10% stream, and then truck this one to the next plant if there is one, or send it with another pipeline. Then you don't have to process all the natural gas flow. So there's actually no limitation for the size.
Fantastic, and we'll probably stick with you here, Patrick. Craig asked the question, how far along is the commercialization of these plants based on these membranes? Can an operator buy one today?
Yes, for sure. Just ask us. We get you an offer and we get to the plant. It's a commercial product. I don't know if you see the background here. So this is actually the plant, which is very small, compact, which in the end it could also be relocated to another site. It's not, the investment cost for the civil construction is quite low. You just can't put it somewhere else. So if the well is depleted, if this well is depleted, you can move it to the next one if it's farther away. So yeah, it's a commercial product. We have it in our portfolio. Ask us. Also, that's no problem.
Okay, and the next question that's come in asks simply, are there any efficient membranes for CO2 and helium separation?
Yeah, I'll go ahead and take that one. That one is a bit of a challenge with the membranes on the market today. So the Sepron membranes that we have commercially available, both CO2 and helium go quickly through the membrane. So they would be difficult to separate with a membrane alone, but that's another way where Lindy's PSA comes in, right? So you can perhaps produce a stream from your well that is almost only helium and CO2. And then the PSA, Lindy's PSA, would be able to polish that helium up to your final purity spec. But that's not to say that next year or a few years from now, Evonik would figure out a way to design a membrane or a new polymer that is able to separate helium and CO2. So we're constantly developing new products, and we invest heavily in this technology. So the answer is today, is difficult with the membrane, but tomorrow maybe not.
Okay, great. And that brings me on to a question I have for you, Alex, if we can stick with you. I'd like to ask, I mean, Evonik's membrane technologies have certainly raised the bar in separation and purification by the sounds of it, which leads me to ask, do you envisage that bar being raised any higher? Do you think there are any further gains to be made in the next generation of these technologies, and could they be on the horizon?
Yes, absolutely. So Evonik is quite clearly pushing to further develop our membrane technology to make helium production and all of our other membranes, but make helium especially even more of a no-brainer. So whether that means new extra high capacity polymers, so your plant needs fewer membranes for the same amount of feed flow, or an even more selective polymer that allows your plant to operate more efficiently or produce a higher level of helium purity, Evonik is already investing into these kind of developments. Membranes at Evonik have been defined as a growth field for our company, so that means lots of time, energy, and resources are being used by the group to improve our technologies even further and meet the growing demand for these products.
Okay, fantastic. And I've got a question from Cliff Kane, which I guess will be put into you, Alex. Patrick, feel free to interject. Cliff says, what are the current specs on this membrane? Is that something you can shed some light on?
It is not at the moment. There is a set of specs for the gas quality going into the membrane to make sure that they don't get hit with slugs of liquid, for example. But the specifics I can't really discuss here.
Okay, sure. We'll leave that one there. Another question's coming from Joel. It's a question for the whole panel, it seems. What do we think about the helium shortage at present? Will the current scenario change shortly? I mean, I think we've kind of covered this, but do we have any extra views to add here?
I'll mention something about that. You know, we have several projects in the works, and in fact, we're working with some exploration people out there that have some projects that are going to be brought online. You know, the biggest problem that's going on right now in the United States anyway is the fact that, you know, our helium reserve is pretty well depleted. So we're only going to get a little bit of helium out of there for the next few years, and then we're going to get none. So that was making up about 20% of the supply, you know. So we can't really crank up any projects. You know, we build these things to work in a plant over a certain period of time. So I remember when, you know, we had this shortage because of the Middle Eastern situation a few years ago. We could only crank up an additional 3% capacity, you know, by cranking everything up. So these things are designed to last for a long period of time at a certain rate. And so unless we actually bring new resources on, we're not going to be able to solve that problem. But look at the technology we're talking about today with Patrick and Alex here, of being able to go out now to a single well, you know, or maybe just one or two wells and put them on a plant. Before, we needed half a dozen wells or more probably to justify putting in a plant, you know, even with just a nitrogen helium mix. So I think we're going to see a lot of helium coming on in the next 5 years, quite honestly.
Great, that's a very good answer there. Thank you, James. We have a question from Nathan Bacchese, which I'm pretty sure I'm going to direct to you here, Patrick. He says, as a reference, what is the helium output capacity of the plant in the background image there?
You mean the output amount of helium?
Yeah, yes.
It's also actually not a limitation because we can process as much gas as there is. The PSA, there are very large PSAs on the market, which is not an issue. I mean, the issue is where to bring the helium, where to get it. But this goes from, I don't know, let's say filling one tube trailer per day to 10 or 20. There's no limitation in the back of the plant, actually.
Great. Okay.
Everything can be sized and designed.
Absolutely. So we've had a couple of questions that I think are more applicable to next week's episode when we talk about some market projections. But we have a question here from Oliver, who asks, rather interestingly, if you're going to exploit the helium primarily and not the methane any longer, does that mean methane becomes the new off gas?
Well, I can answer that a little bit. I don't think so. No, methane still has a use, right? I mean, that's what is heating our homes and running a lot of things. And so we're never going to really uh, not look for methane. You know, we're going to try to find both. I mean, who knows? Now maybe we'll try to find helium. We'll actually find some methane. I don't know. Maybe that's something, you know, kind of a little different twist on everything. But no, the exploration is going on, you know, for both, and it will continue to go on for both as long as there's a market for both. Right? That's my opinion.
Sure. And I'm just going to throw a question here to wrap up this Q&A session. For each of you, just a very quick snapshot. We've talked a lot about helium production, say 10 years ago, and of course today in 2020. Let's look 5 or 10 years down the line. Do you think we could see some really big differences again when we revisit this topic? Should we go to you first, James?
Yeah, I think that we will. I think we already have identified some areas that are being explored right now. And so we are going to see more of a shift to helium being produced as the main product rather than a byproduct of natural gas. I mean, the largest area in the United States for helium production has traditionally been the southwest Kansas, Hugoton, and into the panhandles of Texas and Oklahoma, the Panhandle field there. And that's predominantly natural gas with helium ranging from 0.5% to say 3% quantity, and large, compression type plants, older technology type plants. And that production is declining about 5% a year. And in fact, some of those areas are actually on vacuum. They're actually, producing below at what, normal pressure. And so we're going to run out of that. And so we've got to displace that with other sources. And those sources are going to be helium that is found that is not with natural gas or is with low concentrations of natural gas. That will be the big difference, I think.
Sure. How about you, Alex?
Yeah, I think James is totally right. I don't expect the demand for helium to change anytime soon. We're always going to need MRIs. We're always going to have a need for aerospace and defense. And those markets tend to be insulated from economic changes compared to something like automotive, right? So I think regardless of what might be going on this week or this month, in the long term, there will continue to be a demand for helium. I see the big changes in the future being that so far to date, membranes have kind of been a niche technology. The LNG plants are far and away a more popular or ways to produce helium to date. I think the change coming in the next 10 to 20 years is when we go look for these individual sources of helium, that membranes are going to be the first choice rather than a big, expensive cryogenic plant.
Sure. And finally to you, Patrick, any concluding thoughts?
Yeah, maybe one possible helium source in the future could be that we recover helium that has been used in MRI or in research labs where it evaporates and kind of just goes out of the vent with the air conditioning. And in these cases that you could recover this maybe, and then you don't need that much new helium or fresh helium, which I see could also be then that we reduce the use, or as we use more, but we try to reduce the waste of helium.
Sure. Well, thank you very much, gentlemen. I'm sure all of our viewers will appreciate those responses just as much as we did here. And that concludes our webinar today. We hope you've enjoyed it, and we hope you're leaving with a little more clarity about helium exploration. I'd like to thank all of our panelists, James, Alex, and Patrick. Our special thanks go to Evonik as the sponsor of this webinar series. And of course, thanks to all of you for your time and attention. We look forward to seeing you all back again this time next week for part 2 of the series, when I'll be joined by Phil Kornbluth of Kornbluth Helium Consulting and Mike Corbett of Links Consulting to explore the impact of COVID-19 on helium markets and applications. Until then, thanks for watching.